All right, let's talk about one of the biggest, most mind-bending puzzles in all of science. Seriously, this is a mystery that suggests our whole understanding of reality, well, it might be fundamentally fractured. Like there's a deep crack in the very foundations of physics.
You see, for decades now, we've had this incredible thing called the Standard Model of Particle Physics. Think of it as our official rulebook for the cosmos. It's this amazingly successful theory that describes all the fundamental particles and forces that make up, well, everything. And we have tested it to an absolutely stunning level of precision. It works.
But there's a catch, a huge, glaring problem that just doesn't add up. It's like this one loose thread in the fabric of everything we know, and if you pull on it, the whole thing could, maybe, unravel.
So, what is it? What's this one giant flaw? This is the question that keeps physicists up at night. The reason we build massive experiments like the Large Hadron Collider. It's a cosmic detective story, and we're about to investigate why our universe seems to be built on a foundation that, by all rights, just shouldn't work. Okay, let's dive right in. We're starting our investigation with something that physicists call the hierarchy problem. It's a pretty bland name for what is essentially a flaw in the grand architecture of the cosmos, a crack in creation that we just can't ignore. So what is it really? At its heart, the problem is this. The fundamental forces that run our universe have wildly, and I mean wildly, different strengths. And we have no clue why. We are not talking about a small difference here. We're talking about a chasm so vast, it's like the two great pillars of modern physics, relativity and quantum mechanics, don't even speak the same language. To really get a handle on this, you have to look at the main players in this cosmic drama. And the first major clue we have is this absolutely staggering imbalance in their power. On one side, you've got gravity, the big one. It's the force that holds galaxies together, bends light, and literally shapes the fabric of space-time. And on the other side, you've got the quantum forces, things like electromagnetism and the nuclear forces. They're the ones that rule the chaotic, high-energy world of subatomic particles. And this table here really lays out just how big the problem is. See, gravity is the boss on the scale of stars and galaxies. But when you get down to the subatomic level, it's basically a ghost. It's barely there. The quantum forces, though, they are absolute titans in that tiny little realm. They don't just work on different scales. Their strengths are in completely different universes. And this chart just says it all, doesn't it? It shows the sheer, almost comical scale of the difference. If the strength of the quantum forces was, say, the height of a skyscraper, then the strength of gravity would be less than the thickness of a single sheet of paper. So the question is, why is gravity so unbelievably, ridiculously weak? Our best theories have no good answer. Now, this massive imbalance points our investigation directly at one very specific particle that sits right at the crossroads of these two worlds. The famous Higgs boson. Its bizarre properties make it our number one suspect, or maybe it's our most important clue. You've probably heard of the Higgs. It's the particle that comes from the Higgs field, an energy field that fills all of space. And as other particles move through this field, it's kind of like they're wading through this cosmic molasses. That interaction is what gives them mass. It's what gives the universe substance. Without it, atoms wouldn't form. Nothing would. So yeah, the Higgs is a pretty big deal. So how do we crack this case? Well, physicists have a playbook. First, they map how the Higgs connects with other particles to see if it's playing by the rules of the Standard Model. Second, they're actually measuring how the Higgs interacts with itself, which can tell us about the very stability of our universe. But the most important part? They are hunting for any weird behavior, because quantum mechanics predicts the Higgs's mass should be enormous, trillions of times heavier than what we've measured. The fact that it's so light is the real mystery here, and any little deviation from the script would be the smoking gun. It would be a sign pointing straight to new, undiscovered physics. And look, finding that new physics isn't just some abstract puzzle for scientists in a lab. Solving this whole hierarchy problem has huge implications for how we understand reality itself. As one of our sources puts it so well, this isn't just some minor rounding error. It's a neon sign telling us that our view of the universe is fundamentally broken. It's a major flaw in our blueprint of the cosmos. So why does this matter so much? Well, this gap tells us our standard model can't be the final story. It's like a giant arrow pointing towards something new, something we haven't discovered yet. Solving it could even tell us if our universe is going to be stable in the long run. But maybe the biggest reason is that this problem is the single greatest roadblock standing in the way of physics' ultimate dream, a unified fields theory, a single equation to describe all of reality. And what's really wild is that this isn't a one-off thing. A very similar kind of hierarchy problem,
This strange, unexplained weakness shows up with dark energy. You know, the mysterious force that's speeding up the expansion of our universe? Yeah, that's also bizarrely weak compared to what our theories predict. It's like the cosmos has a habit of building these huge, unexplained imbalances, hinting at some deeper rule we just haven't figured out yet.
And that brings us to the final, really tantalizing question. The hierarchy problem isn't just a flaw, it's a clue. It's a breadcrumb trail that nature left for us, leading us toward a much deeper truth. So, could cracking this one single mystery be the key that finally unlocks a complete, unified theory of everything? We don't have the answer. Not yet, anyway. But right now, at particle accelerators and in the minds of theorists all around the world, the hunt is on. The investigation into our universe's greatest unsolved mystery continues.